Welcome back to Newtonian, and in today's lesson what we're going to be covering is the topic of carbohydrates. Now this is one of the topics in the biological molecules chapter, and this is something that comes up very frequently, and this will lay some of the foundations for other things that we'll learn onwards, such as proteins or even nucleic acids. So the first thing that we need to understand is what exactly is a carbohydrate? Well, a carbohydrate is just an organic polymer which is made up of carbon, hydrogen and oxygen. So the key things that we need to know here is it's an organic polymer, and the atoms that it's made out of include carbon, oxygen, and finally hydrogen. Okay, so these are the three atom types that we have, three elements that make up carbohydrates, and this is in a polymer form. Now, just to clarify what a polymer is, well, a polymer is just long chains of something. So poly means a lot, and the onomer bit comes from the MER bit comes from the word monomer. So let's just understand what a monomer first is. Well, a monomer is just one small subunit. So we can have many subunits. So let's just say 1, 2, 3. These are 3 subunits. Now these individually are known as monomers. Okay. However, when I join all of these together, what I'm forming is a polymer. Okay. A carbohydrate is a type of polymer which is made out of monomers. Now we're going to cover what type of monomers they are in a bit. So just to recap, what is a carbohydrate? A carbohydrate is an organic polymer which is made out of carbon, oxygen and hydrogen. Okay? And that's kind of it with the definition of a carbohydrate. Now let's go on to the idea of what the monomer for a carbohydrate is. Now we know that it's made out of carbon, hydrogen and oxygen. Now what these combine together to form is a single subunit. Now in the case of a carbohydrate, that single subunit is just a monosaccharide. Monosaccharide. Now when I first learnt monosaccharide, that word really scared me. I was like, I've never heard of something like that. But trust me, it's very simple. Let's just break the word down, okay? Now, what does mono mean? Mono just means one, right? Now, saccharide is just a fancy way that scientists came up with saying sugar, right? So, what does this word translate to? One sugar. That's literally it. Scientists just like using complicated language to, I guess, maybe just mess our lives up. But yeah, that's kind of it. Monosaccharide, one sugar. As simple as that. So we know that the monomer, in other words, the small subunit that makes up our carbohydrates, in other words, our polymer, are known as monosaccharides. Now, what are some examples of monosaccharides? Let's use a different color. Now, some examples of this monosaccharides. Now, the most popular monosaccharide that you will ever find is glucose. Glucose. The next one, we know fructose. Now, fructose is this very sweet thing that you sometimes get in sweets as well. And it's, from the name, it's related to fruits. Now, the next one you need to know is galactose. Galactose. Another one is deoxyribose. And finally, we have ribose. Now, if you look at this, I've actually separated these two out on separate sides. Now you might wonder why. Well, the reason is because on this side this group has something in common, and this group has something in common. What can it be? Well, what's in common is that these three have the same number of carbon atoms, and these two have the same number of carbon atoms. So, how many carbon atoms do they have? Well, these three are known as hexo monosaccharides, and the hexo bit means, from we know hexagons, 6 sides. So hexomonosaccharide, yeah, it's as simple as that. It's just 6 carbon atoms. Okay. What about deoxyribose and ribose? How many do they have? Or better, what do we call them? Well, we call them pentose monosaccharides. Pentose monosaccharides. Right, now take a guess, what number of carbon atoms are here? Pentose, pentagon, 5. Right, that's it, literally, right? Hexose monosaccharide means 6 carbon atoms. Pentose monosaccharide means 5 carbon atoms. Now, be very aware of this, that these 6 carbon atoms don't necessarily have to be in the ring. And when we draw glucose out, you'll realize what I mean. And the same goes with pentose monosaccharides. The 5 carbons don't have to be in the ring. They can be, for example, a group that's being attached to the carbons in the ring. Don't make that mistake. I always used to be like, hexose monosaccharide, glucose has got 6 sides, so 6 carbon ring, and you lose marks for that. No, you actually only have 5 carbon. No, I think it's 5. Yeah, you've got 5 carbons in the carbon ring for glucose, and you have attached subgroup which has the other carbon. So always remember, hexose monosaccharides means the whole molecule only has 5 carbons available, and a pentose monosaccharide means the whole molecule only has 5 carbons. Now, to hit the point home, what I'm going to do is I'm going to draw out ribose first, okay? Draw out the structure of ribose. From that, you'll be able to see what I mean. So we've got an oxygen here. We've got this here. We've got CH2OH. We've got HOH here. We've got OH here. We've got H here. We've got H here, and then we've got a H here. Now, these diagrams can sometimes be very confusing because they don't act as a skeletal formula with these subgroups. They, like, when we're learning this for the first time, you're like, yeah, but how do I count the number of carbons? Well, essentially, you've got a carbon here, you've got a carbon here, you've got a carbon here, you've got a carbon here. Yeah. So if you count them, 1, 2, 3, 4. There are only 4 carbons in the ring of ribose. And you've got an extra carbon, which is up here, right? So you can see from this that there's four carbons in the ring of ribose, and you've got an extra carbon as a group attached to that. And that hits the point home that you don't necessarily have 5 carbons in the ring. Instead, you can have the extra carbon as a subgroup. Now, do we need to know the structure of ribose and deoxyribose? That's something that's been very hotly debated, I can't lie. And when I was doing my A-levels, I kind of did say I'm going to just skip ribose and deoxyribose structures because the value you gain from it is likely to be much less than any marks you could gain from that. What I would recommend, however, is to learn the structure of glucose. And that came up in my A-levels too when I was doing them. I still remember looking at that structure and I was like, yes, memorize that. So I would recommend remembering the structure of glucose, and that is something that we will go over. Yeah, okay. So I won't draw up the structure right now because I want to teach something else when I draw the structure of glucose, but I'll cover the hexose monosaccharide bit again. But I hope you understand what this hexose monosaccharide and pentose monosaccharide means. There's 3 hexose monosaccharides, glucose, fructose, galactose you need to know. There's 2 pentose monosaccharides, ribose and deoxyribose. We will cover them in greater detail later on, but yeah, we can just skip them for now. Not much point. Cool. What are we going to do now? Well. Now, okay, so we covered monosaccharides, right? What happens when I combine 2 monosaccharides together? Let's have a look. So I've got my 1 monosaccharide here. I've got another monosaccharide here. Okay? We combine these 2 together. We've got a bond between them. Now you've got 2 here. So we initially had a monosaccharide, right? And that was because there was only 1. What happens when I put 2 of these? We know that the thing in front tells us the number. So if I got 2, what's the thing that we put at the start for that? Oh, it's di, right? Di. So this, when you've got 2 monosaccharides together, joined and bonded together, you call it a disaccharide. What do you call it? A disaccharide, because it's got 2. In the same way, what if I add another? What if I add another monosaccharide to this? Well, what do we have here? We've got a chain of monosaccharides, multiple monosaccharides. So what are we going to call this? We're going to call it trisaccharide. Well, that's what I wanted to call it, except that's not what you call it, unfortunately. Instead, you just call it a polysaccharide. And you pretty much do that if I add another one, and so on. You just keep calling them polysaccharides. Okay? Yeah, you don't need to remember tri, quad, whatever. So monosaccharide, disaccharide, polysaccharide. That's kind of the order you need to know. Well, not even need to know, you can work that out. Not much of a problem. But let's just look back at our disaccharides, okay? What are some examples of these disaccharides? You know, let's rub all of this out because we're gonna have to do a bit of writing. You know, with bio, this part, there's a bit of memorization that you kind of need to do, unfortunately. And there's not much going around that. So, what are some examples of disaccharides? Disaccharides. Example number 1. Example number 1 is sucrose. Example number 2 is maltose. Example number 3 is our lovely lactose. Well, not necessarily lovely for people who are intolerant to lactose, but yeah. Oh, damn it, my colour scheme. Yeah, it's fine, who cares? Anyways, so sucrose. Let's focus on to sucrose first. So, what makes up sucrose? Let's see. Where are we? Okay, so what are the 2 monosaccharides that make up our sucrose? Well, we've got glucose. Glucose was a monosaccharide, as we learned. Glucose plus fructose. What makes up sucrose? Glucose plus fructose. The end. What about maltose now? What makes up maltose? Well, maltose conveniently is made out of only one type of monosaccharide joined together. What can it be? 2 alpha glucoses. Now I will go over what alpha glucose means just in a minute, right? Just remember alpha glucose, okay? 2 alpha glucose make up maltose. Yeah, just don't question it. We're gonna go over it, okay? What about galactose? Sorry, lactose. What makes up that? Lactose. Well, lactose is made out of glucose, and this can be either alpha or beta. I will go over what alpha beta means. Just remember it, please. Glucose plus what? Galactose. Okay, please memorize all of that. I know it's a pain, but you're gonna have to do it. There's no way around it. Just do it. Yeah. Right, so you got sucrose. Sucrose is made out of glucose and fructose. Maltose, made out of 2 alpha glucose molecules. Lactose is made out of glucose and galactose. Okay, the number of O's there is, it's crazy. Just read it. Yeah. It's probably better than me reading out too. Yeah, just realized. Okay. Now, what about the alpha and beta thing that I was talking about? Should we go over that? Yeah, I think that's a good idea, yeah. Okay, so yeah, you can pause, rewind, whatever you want. Just memorize that, please. Don't lose the mark on that. Okay, next thing we're going to cover. We are going to cover what alpha and beta glucose is. Now, when I came to A-level, I did not know what the sign for alpha or beta was. So this is what the signs are. Right, I'll write it out for you guys. Alpha glucose will always have a sign like that. That thingy looks like an A as well. It's just, yeah. Beta is probably one of my favorite ones because it's a B. Right, so now what I've done is I've got the 2 structures. So I've got alpha glucose and I've got beta glucose here. Now, what exactly is the difference? And that's what we need to figure out using these structures. So if you have a look at the alpha glucose here and you compare it to the beta glucose, you can see that nearly all of the structure is kind of the same in both of them. So what's different? What's different is this here. Your OH group in the alpha glucose is at the bottom, whereas in the beta glucose, the OH group is at the top. So essentially what happens is your OH group switches around in the beta glucose. In your beta glucose. So in the beta glucose, it's at the top, and alpha, it's at the bottom. It's a bit annoying the way they've worded it, because alpha you'd have thought as being at the top, and beta at the bottom, because alpha is number 1, beta's number 2, but it's the other way around. That's the way I used to remember it. I would be like, well, they're not going to try and make our lives easy. So I know alpha, it's probably going to mean the second one, and beta, the first one, because they never make our life easy. So that's the way I kind of memorized it, but you can go about your own way. And please do learn the structures of glucose. You kind of need to know it. And please don't try and learn it in a day. Just try and draw the structure every night, and over 30 days or something like that, you end up learning the whole thing. Don't do what I did and try and cram it in one day. It doesn't really work. Well, it does, but not fun. Anyways, now the next thing I want you guys to observe is the presence of these things. You've got so many OH groups here. Now, what's the significance of these OH groups? What does OH mean? Well, OH, we saw in our last lecture on water, we saw that oxygen is partially negatively charged and hydrogen is partially positively charged. What does that mean? Anything that has OH groups, it's a large statement, but in bio at least, anything you'll come across with OH groups will be polar. What will it be? It will be polar. In other words, our lovely glucose friend here is also polar, right? Glucose is polar. And if glucose is polar, what does that mean? We know that water is polar, glucose is polar. That means glucose, water have attraction. If glucose and water have attraction, what does that mean? Well, that means glucose is soluble in water. So, glucose soluble. And if glucose is soluble, what does that mean? Well, that means that it affects water potential. See, this water potential thing will come along everywhere. It'll sneak in, right? If it affects water potential, it affects osmosis. And if it affects osmosis, what's the problem here? The problem here is if it affects osmosis, and that means me trying to cram a whole load of glucose in a cell will essentially just mean water moving into it. That won't really happen. Instead, you'll just have your glucose diffuse out of your cell. But yeah, you just need to remember that glucose affects osmosis. Yeah, just remember that. And that's kind of it, to be honest. So we've learned alpha, beta glucose, and we've covered the fundamentals of carbohydrates. We've covered what monosaccharides are. Monosaccharides add up to build disaccharides. And then if you add up more monosaccharides to disaccharides, you end up forming polysaccharides. The last thing I want you guys to remember is what happens as an overview in reactions where we're adding monosaccharides together. So you might be like, what does he even mean when he says that? It's a massive mouthful, isn't it? Well, this is what I mean. Okay, so we looked at the start of the lecture, we said that we have a monosaccharide, we have another monosaccharide. And what I said was when I join these together, we form a disaccharide. But I just drew a line to indicate a bond. What is that bond? Now that's the big question. Now this bond here, I probably need a bit of duster, don't I? Well, this bond here is known as a glycosidic bond. So let's draw this with a glycosidic bond. Glycosidic. This bond between two monosaccharides is known as a glycosidic bond. Now, what happens when a glycosidic bond is being formed? Well, when a glycosidic bond is being formed, essentially what you have is you've got two OH groups, okay, of these monosaccharides. Now they're next to each other. Actually, should I draw it like this? Okay. You've got two carbohydrates and they've got their OH groups, right? And these two carbohydrates are facing off each other. Okay? One carbohydrate is here, the other is here. Now in this reaction, what you have is one of the carbohydrates, it gives off its OH and the other gives off only its H. Now what you have here is you've got two hydrogens and one oxygen. And what does that form? Let's think. H2O. Yeah, water, right? So you form H2O, water. If you're forming water, you know, in the winters on your windows, right? Inconveniently, you've got water forming. They're going to be like, why is this guy going off in a tangent? And when you have water forming on your windows, what do you call it? Condensation, right? And that's exactly what type of reaction this is. When a glycosidic bond is being formed, guys, it's called a condensation reaction. Condensation reaction. Lovely. When monosaccharides join together, you have a glycosidic bond being formed between them, and when a glycosidic bond is being formed, because your H from the first carbohydrate combines with an OH from the second carbohydrate to form a lovely glycosidic bond. And whilst it's doing that, you will have your H from here, from one, and OH from the other. These will form your H2O. Now you're going to be like, yeah, that's cool, but there's one oxygen left here on one of the carbohydrates. So what happens? Now this is something that's very interesting. What we have left is, so we know that there's going to be a carbon here on the carbohydrate, and there's going to be carbon here on the carbohydrate. Now on one of the carbohydrates we have an oxygen left. What happens now? Well, this is the key to the glycosidic bond. The glycosidic bond isn't a line. I'm sure you guys would have guessed that, right? Well, a glycosidic bond is essentially this oxygen. This oxygen will bond to the other carbohydrate's carbon as well. Right, so this whole thing here is our glycosidic bond. Now, because it's kind of like an oxygen, and well, scientists imagine you could drive a car over this, right? Okay. Just imagine you can drive a car over this, okay? So scientists saw that you can go from carbohydrate 1 to carbohydrate 2, you can go in a car, right? Because of this thing. That's why they also call this an oxygen bridge. So a glycosidic bond can also be referred to as a oxygen bridge. It's essentially a glycosidic bond because this is an oxygen and it's kind of like a bridge on which you can have a car zooming past. Lovely creativity. Who said science doesn't require imagination? But yeah, that's kind of it, isn't it? So you've got your glycosidic bond and how it's being formed. A glycosidic bond is formed through a condensation reaction. What about if I wanted to break the glycosidic bond? What do I do? Well, the thing is, at least this is going to be quite simple. So when I formed the glycosidic bond, we call it a condensation reaction because of water. So clearly, when I break the glycosidic bond, it's something got to do with water again. So this is my glycosidic bond. Now how am I going to break this guy? Well, what I need to happen is I need it to go back to this form. This is the form that I want. Right. How can I change this thing to this thing? What's the key here? The key here is I need to add the missing elements. Now, what are the missing elements here? You're missing 2 hydrogens and you're missing 1 oxygen. In other words, you're missing a water molecule. So all we do is we take a water molecule, H2O, and we add it to this. Now, when we add it to it, after I add it to it, plus an enzyme, that enzyme will cause for the bond to be broken, the glycosidic bond to be broken, and it will use the 2 hydrogens and 1 oxygen to reform this structure here. Once it's reformed that, voila, you've got your 2 carbohydrates back. Now, once you've got your 2 carbohydrates back, we need to name this. And what are we going to conveniently name this? Well, because it's got something to do with water, we're going to call it hydro. And because we're breaking, we know in electrolysis, right, the lysis part means to break. In other words, hydrolysis, hydrolysis. Okay? So that's essentially our answer. Hydrolysis is where we break the glycosidic bond. Okay, hydrolysis is where we break the glycosidic bond, whereas condensation reactions are reactions in which we make the glycosidic bonds. Condensation reactions require water. Condensation reactions release water, whereas hydrolysis reactions require water. Okay? I hope all of this made sense and you gained something from the video. Please keep learning and please keep watching Newtonian. Thank you so much.